at 2.2, limits involving infinity, day 2. And at the very top of your page, it said, say horizontal asymptote warm up. Yes? All right, so it says if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. There is what we call a slant. In order to find or calculate a slant diagonal, we need to go back and use something called long division. So we have x squared minus x minus 7. And we're going to long divide that into 3x cubed plus 2. Anytime you're long dividing and it's missing variables, you must put a placeholder of 0. All right. So, in order to long divide, you ask yourself what the very first one is to the last one. So we would say, okay, what do I have to multiply x squared by to get 3x cubed? Well, 3x. So then you take that 3x and you multiply it back. So you take 3x times x squared to give you 3x cubed. 3x times x is negative 3x. 3x times 7 is negative 21x. You change the signs of each term. The second one, yeah. So the rule of thumb is once you multiply, you subtract. So we change the sign of every term. Your first term should always zero out. So then I get 3x squared plus 21x, bring down the 2. Multiply again. So what do you multiply x squared by to get 3x squared? Yep. So 3 times x squared is 3x squared. 3 times negative x is negative 3x. And 3 times negative 7 is negative 21. Change your signs. So you zero out. You get 24x plus 23. At this point, since the first term is x squared, and this is now x, this is my remainder. So you get 24x minus or plus 23 all over x squared minus x minus 7. That's our remainder. The equation for the slant diagonal, and again, it should make sense. Think about slant. It's kind of like you think of something tilted, slanted, etc. So the equation of the slant diagonal is 3x plus 3. So what that means is if I were to graph this at 3x plus 3, this is where your graph kind of looks like it goes towards something, but we never see what it's going towards. So these are the graphs that kind of look like this, where they're like approaching or slanting near it. Those are called slant asymptotes. I didn't actually check that, so that may not accurately be your graph. I was just kind of showing you what it would look like. You could graph this to see it. So if you went to your graphing calculator, went to y equals, typed in your equation, you should be able to see on there kind of where that graph fits in. You could actually even graph 3x plus 3 and see how like the second graph line approaches it but doesn't reach it. Good. Okay. Then let's talk about end behavior models today and graphing them. All right, so you should be able to see this in a second. We are, again, looking at infinite limits. It won't erase. Give it a minute. Maybe. I don't know why it's stuck. All right. Take a minute and read that on your paper, not on mine, because clearly my board is going crazy. And we'll touch base in a second. So it says for numerically large values of x, we can sometimes model the behavior of a complicated function by a simpler one that acts virtually the exact same way. The function g is considered a right end behavior model if we look at g that way. Try this again. Okay. The function g is a left-hand behavior model for f if and only if. So we have two things that are going to happen. It is a left or right end behavior model if and only if the limit as x approaches infinity of the two functions equals 1. Left end behavior would be negative infinity of the two functions equaling 1. So what end behavior models really say are, okay, let's take this complicated function and simplify it. So we looked a little bit at an end behavior model earlier when we talked about comparing the two complicated functions with each other before and looking at the horizontal asymptotes. So let's say f is the function given to you. So you have 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6. You really don't know what that function looks like graphically. But if I asked you what 3x to the fourth looked like, you're more likely to be like, oh yeah, I know what an x to the fourth looks like, just like you could say I know what x squared looks like. Well, that's what end behavior models kind of do for us. They say, okay, f and g might not start the same, but at the end, as both get infinitely larger, they're going to act the same. So as both get infinitely large, they're going to act the same. So what we're going to do is take out our graphing calculators and put this into our graphing calculator. So go ahead and take our graphic 2 on x and make your y's -5 to 20. Okay. So at first, these don't appear very close to each other, right? They look kind of farther apart. The red one's up a little bit. Agree? Oh, I froze you. Okay. Now, change your window. Zoom out. Go back to window. Make your x values -20 to 20. And make your y values -10,000 to like 500,000. Make sure you change your step to like 1,000. Now when you look at your graphs, do they appear different or the same? Do these look the same or different? They look really, really, really close to being the same, correct? You can hardly see any differences. That is what end behavior models tell you. End behavior models tell you as x's are getting bigger and bigger, either to the positive or negative infinity, these two functions are going to behave exactly the same. So what can I say about this? If I asked you what is the limit as x approaches infinity of the top one, which we called f of x, what's happening as f of x is getting really, really big? Where's this graph going? Where's the red one going? Okay, so this equals positive infinity. Where is the graph of G going? Can't recover from that. So, would infinity divided by infinity equal 1? Are they the same thing? Yes. So do these behave the same? Yes. Do they follow the end behavior model? Yes. Now let's talk about algebraically how to compare them. Okay? Where's my PowerPoint? Okay. So graphically, we confirm they behave the same. Analytically means to use your algebra. So if I wanted to algebraically compare these, that's like doing the limit as x approaches infinity of one over the other. So what we're going to do is go back to the days where we divide top by bottom. So take the top and divide each piece individually by 3x to the fourth. Three x to the fourth over 3x to the fourth becomes 1. Then you get 2 over 3x plus 1 over x squared minus 5 over 3x cubed plus 2 over x to the fourth. But think about something divided by infinity. So if I had 2 divided by infinity, is that number going to be big, small? 2 divided by infinity. Super, super duper small, right? So anything over infinity in terms of a limit becomes 0. So the limit as x approaches infinity of 1, well, the limit as x approaches anything of a constant is always the constant. So limit as x approaches infinity of 1 is 1. The limit as x approaches infinity of 2 over 3x would be like taking 2 over infinity, which would be 0. 1 over infinity squared would be 0. 5 over 3 times infinity cubed. 2 over infinity to the fourth. So again, algebraically, we have shown that the limit as x approaches infinity of f over g becomes 1. Yep. Like split them. So if you split them, you'd still end up getting what we kind of said previously, infinity over infinity. The only reason it won't work forever like that is because sometimes your f and g's won't be as pretty. Like it won't be 3x to the fourth over 3x to the fourth. Yeah, I won't have you compare them graphically. The graphical comparison was more to get you to visually see what we're going to say algebraically. So like I wouldn't have you kind of do all that zooming on a test. That's more just to help visualize. Anytime you graph on your test, it's not going to be for something like that. Did you just hit your funny bone? What? All right, find an end behavior model. So like I said, it won't always be as simple as the last one. It says, find an end behavior model that would work for this function. So we have f of x equaling, we're trying to find a g of x. So we have 2x to the 5th plus x to the 4th minus x squared plus 1 all over 3x squared minus 5x plus 7. So how do we think this function behaves as it gets really, really, really big? Well, g of x would be the polynomial that exists within this. So up top, our highest powered function is 2x to the 5th. Being divided by 3x squared. So as this graph gets really, 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 really big, it's going to behave like 2x to the 5th over 3x squared. It's going to behave by its highest powered polynomial functions. So that means that this is really going to behave like 2/3 x cubed. So the end behavior model for f of x is 2/3 x cubed. And if you were to put both f of x and that g of x into your graphing calculator, as you zoomed out, we would see that they behaved the same. If they behave the same, that tells me that you could now answer these two questions about f of x. As x gets negative, what should f of x go to then? How would 2/3 x cubed behave? Chase? Perfect. And as x got big, then f of x should also get big because 2/3 x cubed gets big. So these answer those questions about what is happening as x is going to negative infinity and infinity. You're simplifying a complicated polynomial function into a single monomial term to understand its end behavior. So again, this is end behavior. Sorry. There we go. Oh. What would be the end behavior model for this function? Go ahead, Chase. Exactly. So I'm not going to call it f because that confuses us. So yes, the end behavior model for this function is 2/5. So what does that mean as we look at the limit as x goes to negative and positive infinity? It's 2/5, exactly. So that means this function has a horizontal asymptote. So g of x has a horizontal asymptote where? at y equals 2/5. Because the exponent here and the exponent there match, therefore there's a horizontal asymptote at the coefficients. So it's all sort of coming together. This is like the missing piece of your puzzle. It's that piece that you kept turning and twisting and couldn't find it. Well, now it fits into its spot. The end behavior for model is the horizontal asymptote of the graph of G. Bring on the exponentials. So the constant E is defined as the following for its limits. So we can say that the limit as x approaches E of x will always equal infinity. The limit as x approaches infinity of E of x will always go to infinity. So here's E of x. It's this blue graph. So as E is getting bigger, it's going to infinity. The light green graph is E to the negative x. So that follows these limits here. So again, you're just kind of copying down those 4 limits. Okay. So how do exponential functions behave? So it says let f of x equal x plus e to the negative x and show that the function g of x is its right end behavior. So e of x functions do not behave the same on the left and the right. And can't you see that here? Is the end behavior model on the left going to be the same as the end behavior model on the right? Over here, it's going to 0. Up here, it's going to infinity. For that reason, we have to actually look at 2 end behavior models. You look at an end behavior model as x is going to infinity, and we look at an end behavior model as x is going to negative infinity. And again, our end behavior models, to prove they match, need to equal 1. So it's giving us f of x and g of x. And it's asking, does x represent a right end behavior model? So it's asking me yes or no. It's not asking me what the limit of x going to infinity of f of x is. It's asking for its end behavior model. So that means this kind of becomes 1 plus 1 over x e to the x. Because you take the x, split it under the 2, x over x is 1. E to the negative x drops down. So the limit as x approaches infinity to 1, well, 1's a constant, so it's 1. 1 divided by something really, really big is like 0 because it's 0.01. So this is 1. If the answer is 1, then this is yes. G of x equals x is an acting right end behavior model. So what that means is the limit as x goes to infinity of f of x will equal the limit as x goes to infinity of g of x, which in this case is infinity. Because their end behavior models are true, then their limits as x goes to infinity are the same. So f of x divided by h of x now is supposed to represent the left end behavior model. So now I have the limit as x approaches negative infinity of 1 over x. Well, it's being divided by e to the negative x, so that pops up top. And then e to the negative x over e to the negative x becomes a 1. Going back to the chart you just had, e to the x, so e going to negative infinity, ignore the little writing on here, as e goes to negative infinity, what's it going to? 0. So as e goes to negative infinity, it's going to 0. So 0 times anything is? Good. 0 plus 1? So does this behave the same? Yes. So that means that the limit as x goes to negative infinity of f of x equals the limit as x goes to negative infinity of h of x. And we know that the limit as x goes to negative infinity of e to the negative x is actually infinity. Almost done. All right, so absolute values are special because absolute values, if you think about what their graph looks like, are a v. So if you think about a limit of an absolute value, what is happening from the left versus the right? From the left, we're approaching 0. From the right, we're approaching 0. So it says, show that the limit as x approaches 0 of the absolute value of x would equal 0. Well, in order to show that, you would need to not be able to graph it. You need to show analytically what that means. So analytically, you need to know that the absolute value of x is actually a piecewise function. So it's the absolute value of x is really negative x and x. And we'll say it's negative x for all x values less than 0. And it would be x for all x values greater than or equal to 0. And it doesn't matter where you put the equal to, because that's really like saying the limit as x approaches 0 from the left and the limit as x approaches 0 from the right. Because in order to prove that the limit as x approaches 0, you need to prove that the left-hand limit equals the right-hand limit. So from the left, that's like taking the limit of negative x. From the right, that's the limit of x. So negative 0 equals 0. 0 equals 0. So the left-hand limit equals the right-hand limit. Therefore, the limit as x approaches 0 of the absolute value of x is equal to 0. There will be absolute values where that may not always be the case. So this directly falls into the next example, which is the limit as x approaches 0 of the absolute value of x now divided by x. So we just said that the limit of x approaching 0 of the absolute value of x was 0. So how does this become dne? Well, now what's happening is the piecewise is manipulated a little bit now. Now your piecewise function is being changed. So the limit as x approaches 0 from the left, and the limit as x approaches 0 from the right, well, from the left, it's still negative x. From the right, it's still x. But now our function is being divided by x. Which means this really acts like -1. And this really acts like +1. And the limit of a constant is always equal to the constant. So the left-hand limit is -1. The right-hand limit is 1. Does the left-hand limit equal the right-hand limit? No. So if the left-hand limit does not equal the right-hand limit, then the limit does not exist. If you were to graph this function, it would look something like this. Just in case you want to know what it looks like graphically. Okay, and last, show that the limit as x approaches 0 of x squared sine 1 over x is equal to 0. So once again, the minute you see a 1 over x inside a trig function multiplied by a polynomial, you need to think squeeze theorem. You just need to think, okay, this is a function in which I have two outer functions being smushed around it because of the range of sine. So break it down into the limit as x approaches 0 of x squared times the limit as x approaches 0 of sine 1 over x, which really is like saying the limit as x approaches 0 of negative x squared is less than or equal to the limit as x approaches 0 of x squared sine 1 over x, which is less than or equal to the limit as x approaches 0 of x squared, because the range of sine 1 over x is -1 to 1. So since the limit as x approaches 0 of x squared equals 0, and the limit as x approaches 0 of -x squared equals 0, by the squeeze theorem, the limit as x approaches 0 of x squared sine 1 over x is equal to 0. But I have to check the what? Because you have to show why it's equal to 0. And it's equal to 0 because the outside limits are equal to 0. Because of the triangle inequality theorem right here that says the outside limit's 0. So if 0 is less than or equal to, and we don't know what this is, and it's less than or equal to 0, if the two outsides are 0, the inside has to be 0. Okay. So